Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Kirk Gray.
And this is Fred Schenkberg. Well done, Kirk. It actually you have a radio voice sometimes, you know that?
Maybe I could be a DJ. Who knows?
Yeah.
Yes. People have said I like my voice, so and I listen to the podcast. It sounds okay.
Well, that's I think a criteria to be on radio or do recordings. I cringe every time I hear my own voice, even though Diane tries to make it, sound better with all the magic she does on her end. Right. My wife does the editing for the podcast, so I don't have to listen to my own voice, but thankfully she does.
Yeah, I have to listen to them when I do the notes. So
yeah,
I do hear both of us talk.
So that works out great. So anyway, hey, we got a question, and I knew it was right up your alley, so I'm glad we had a chance to chat.
We love questions.
We love questions. But this it reminded me of I think one of the very first episodes we did. It was about how do you do HALT? What is this HALT thing kind of thing. But this question was basically, they admitted they'd listened to some of the episodes and they heard us talking about HALT and they said, well, we think this is something we need to do. So is it really just I take a couple of samples and go find a HALT lab and give it to them and then they run with it? And I knew your answer for this, and I suspect I know what the answer is, I should say.
Absolutely not. Yeah.
That's my first answer. And I was just talking to Chris about a similar question, but it was on an aging study. Is do you know of a lab that can design and set up this test for us and run it for us? And it's Chris's take on it was, I think, similar. What we're going to talk about was, no, you actually need to do a little thinking first. You can't outsource the critical thinking part.
No,
you still need to ask the right questions and do the pre-work kind of stuff to make this work.
Yeah, and especially with HALT.
Yeah,
it's a discovery process, and you're the one that's going to know the product. You're the one, your company's the one that knows what the past failures have been and the history. And you're probably not going to tell a lab all the things that you suspect may happen, but you can't anyway. We'll go ahead, but it's a very, hey, I learned this new idea. Let's go do it. Let's find a lab and do this. All we have to do is give it to them, and we'll
get a report.
We'll get a report or whatever. And this lab, unless they've been working with your products for years or have a real detailed knowledge of its function and its capabilities and its past history, it's not going to be very useful to you. And besides that, before you go to the lab, there's many, many things that you have to do within your company to be able to get any potential success out of it. And there's so many paths that you have to apply to convince and show the relevance of this, because it is so difficult for companies that are oriented toward traditional reliability and models and calculations to understand why you would want to improve the margins beyond the spec and beyond what they anticipate is the worst case use environment, which is always incorrect and very hopeful.
Yeah.
Because they're always very optimistic about how the product will be used and customers will pay attention and be,
treated with kid gloves and,
absolutely.
First thing they do is put their phone inside of an otter case or some, duct tape or something to keep it all together.
Right.
But so just on that point though, is one of the things that popped in my mind is that, they got the idea and they got, go give it a try, and they're ready to go. And, for whatever reason, there's all that. But the first thing that came to my mind is you're going to come back from this lab. The lab report's going to come back and it's going to say, well, it failed. You have a spec of 40C on your product for upper operating temperature, for example. Right. And the first failure is at 80C. And I think that's what you were getting at, is the first thing they're going to say is, well, that's about spec. We don't have to worry about that.
Right.
And it's a signal that, well, to be blunt, you just don't get it.
They don't get it. No.
And that's what I think you're going after here.
One of the examples I use is something like that, where they take one sample or two samples. One goes to 80 degrees, and that's its operating limit. And the other one is 120 degrees, and it's its operating. Same product, okay? Right. And, okay, each one will say, well, it was above spec, and we're not going to investigate it. So you've got to have so many backup resources behind after the halt or during the halt to know if that's a manufacturing defect, if that was a design, it's inherent in the design,
or a measurement error, or
in a very wide distribution, one component that has a value that changes that limit quite significantly, and you test 5 and you get 3 that'll operate 120, 115, maybe 121, 25 degrees, something like that. And then you get that one at 80. Well, then you have something to investigate.
Yeah.
But also, before you go into this adventure, you've got to get your management to see, either through past failures in the field or something that's been painful to them, financially especially, not only embarrassing to the market and public, just like this, we talked about the keyboard with Apple. You replaced it, had a $50 million lawsuit, but still won't admit to any liability to. But you've got to find out why that failed, and then show that that if you had done this test to an extreme level, or when it stopped operating, you would have probably discovered this in having at least 5 samples or something to that effect. Or you can take intermittent, I've suggested this recently to people that attended my webinar. Get some units from the field that are NDF, and you're going to have to get a lot of them. You may have to get a lot of them, but what else are they going to do with them? Do they reship them out? Anyway, Get the ones that no defect found and put them under some stress, especially the digital products, people that are into wireless communication and things like that. They need to put them into a chamber, run those standard tests that you ran on the bench against many of those NDFs, using your software, your test software, whatever, that pushes the bound, operates it in all capacities, and do it at extreme temperatures with digital systems. You will find that there's about 30, my experience was about 1/3 of them will show some kind of problem under those conditions, and many times, and a lot of times, if you have details of what the customer reported, it will be very similar, either blue screen of death, or just failed to operate, or showed this error. That will show up, and then you go to your management, or you go to the design engineers and say, that problem we had that cost us about $2 million in the field, and we had to have a 5% swap out, of these boards, whatever. Okay, what was that costing the company? What did that cost us? Well, it was maybe a $2 million problem. How much is it going to cost to have a $200,000, maybe $300,000, $400,000 by the time you set it up, that will be able to give us is essentially a time machine for this problem, and that we can discover in a chamber. And who knows? I'll go prove it in this lab if you want me to.
Yeah, no, I agree with you. It's a great technique to show that you can find a problem that you should have found. But HALT's a particularly good tool to find the things you don't know you're looking for. And if you wait for your customers to find it, it's not good.
But if you don't do this before you go into the HALT program.
Yeah. We don't always have that luxury of an existing product with field failures and say, hey, look, we would have found all these things rather than scrambling to fix it after. So there is a case, another way to create the justification is that, and we used to do, when I was at HP, we used to do these like lunch and learn type things. And we get somebody in that knew a lot about fatigue cracking or corrosion or about this, and would just talk through the nature of a failure mechanism.
Okay.
So it was a lot of fun because you got to see really cool pictures of really ugly dendritic growth on stuff and things like that. Really pretty, I should say, beautiful blues and greens.
And that's solid evidence. That's real. You can look at it and see.
But it was one of these things that, I mean, there's so many different products and so many different environments. The intent of the discussions was to create awareness of the nature of different failure mechanisms. And even though you see it at 80 degrees C, it still occurs at 20 degrees C. It just takes longer. Right. And so a lot of different things we talked about, and when we talked about failure mechanisms, like vibration, if I'm still creating a vibration that's still in the elastic range, I can change the magnitude of those vibrations and stay within elastic range. And mechanical engineers are going, well, it should be just fine. This is right. Well, here's the failure mechanism that we get. And it just takes longer when we use a smaller hammer on it. If we use a bigger hammer, it's the same failure mechanism. It's just faster. And so I would point back to a lot of those kinds of discussions and educational pieces and how things fail, which is always fun to talk about with engineers, and especially when it's their product. And then say, that's what we're doing in HALT. We're trying to expose those things that are going to occur in our normal use, but just take a little longer. And we're trying to find those before they become a problem, or we're exposing manufacturing defects, or we're exposing this, or design errors. But if we don't know about it, we can't fix it.
I know, but they got to know that mechanism has been in their product before, or they've seen it, or it's not relevant to them. Because
I disagree. No. One of the best ones I ever did. Yeah, no. One of the ones I have two stories, and you've heard both of them, but one of them was a handheld game controller type of device in some unique design for some unique game they're trying to sell, and the circuit board was inside the cylinder and only anchored on one end of it. So it's a long, thin, think of it as a diving board inside a cylinder. Right. And the mechanical engineer is like, well, circuit boards are so wishy-washy. I don't know how to attach that without creating stress on it and all that other stuff. So I'm just going to attach it at the end. It'll be fine. Well, one of the use applications was holding this device and clapping. And it had a sensor in it that could tell if you were on the beat or not, kind of thing.
Yeah, right.
And they're so you're slamming this thing together with your hand. Right. There's going to be vibration. And vibration on a circuit board is usually not a good thing. Oh, it won't be enough vibration. It'll just do this. It'll be a single. Right. And so I said, let's do a clear case and video it. Okay. And until I had the video, he didn't believe me. And he dismissed the finite element analysis that showed the nature of the vibration. Oh, that'll never happen. That was a bad simulation. He just kept denying it until I showed him the actual video of it. But then we took it to HALT, and said, no, trust me, we're going to go run this test and see what else we can find in this thing. He said, haven't you broken it enough yet? And I'm like, no, we haven't yet. Come on, let's go find out. And they had a battery wire that came off the battery chamber, a stiff wire, that at the last minute, they moved it about an inch where it would attach to the circuit board. And it's not a mechanical hold to put a thin wire soldered into a circuit board. It's in the middle of a ramp that it would dampen the vibration a little bit, but not completely. And where they bent the wire and how they assembled the thing, the wire rubbed on the surface of the circuit board. And would you know that the opposite polarity trace was right under the solder mask?
Right.
And so shorted out within about 4 minutes in the test. And we opened the thing went off, and it was like, all right, what's going on? And you open it up and you can smell the phenolic burning because the battery discharged completely into it or across it. And we took it apart and we could see the rubbing. It was obvious we didn't even need a microscope. So I sent some pictures back to the designer and I said, I think this is a different problem, but it's still vibration, kind of thing. And he was blown away at that point, but it was because of that first one showing him says, here's when we suspect, and it wasn't, we didn't do HALT. We just took it in the lab and and
Right.
just to see
You
how it
showed him a
moved.
failure mode
Yeah.
that you could reproduce and accelerate. And this is the very first controller they had ever made. They didn't have any history. See,
No. It was a unique design. It wasn't like the classic PlayStation or Game Boy, type controller. It was kind of looked like a microphone.
Right.
But it had a bunch of extra electronics.
It had accelerometers in it, and it had lots of things in it.
It was really cool.
Right. And you showed probably a very relevant failure before that. But if you'd gone well outside, and you just showed the vibration, physical, obviously you were able to do that, convincing him. But I think there's so many cases that you can't physically see that.
No, if I was at 50 GRMS, they would have said, nobody's ever going to see that. And we happen to see the one.
Right. For a handheld device that uses a game controller that is going to be dropped and you said clapped. And
we even tested it for, will it fracture if you sat on it? Because we didn't want to cut somebody's butt apart and get sued for it. that kind of thing, any outdoor consumer or handheld device for consumer use is absolutely going to be overstressed beyond its limits by somebody somewhere. And so it was a fun product to work on. The team was actually pretty accommodating. It's like, well, we brainstormed for about 20 minutes one day in one of the staff meetings as well. How many ways can this be stressed? And it was phrased that way, which is another thing you should do before you go to the HALT chambers. Well, what kind of stresses do you are relevant to apply to this thing?
Right.
Now, this was an electronic component, but handheld. And so drop is a good one, or shock, or, all these kinds of things. We even had a long discussion about, well, what happens if somebody is like, there was one product. It was, what was it? I don't even remember what game station it was, but you could do golf swings, and it was a little wrist held or handheld thing, but you could do tennis.
Wii.
Yeah. And they had a long debate about
Wii. Great little game. I had one.
I agree, but it was, do we put a wrist strap on it or not? And it was, and the fear was, and I guess there were some reports of people throwing their controller through the TV kind of thing into walls.
They
did. They did. I noticed you didn't. You said you didn't do that, so that's good.
No. But they got dropped and they got thrown, and it was a real action game with the accelerometers and the controller.
Yeah.
So it's expected those controllers received a lot of shock and vibration and being possibly dropped and thrown against a wall. And again, there's a limit to what you can do to protect yourself from those.
Oh, right.
Extreme. It goes out a window, drops to 6 floors, downstairs. It's not going to survive.
So part of the discussion was, one of them is in order to understand if you have margin or not, it's like the temperature one. Well, we didn't really know if 40 degrees C was relevant or not. And we gathered a bunch of weather data basically and said, in the markets we're going to be at, this is going to see 45 C on occasion, and we had a percentage for it. We did a whole distribution for it, and said so. And it was a trade-off. Part of the information of like, do we need to worry about that or not? Mostly we didn't worry about it, but if we would have saw failures at 50 C in the chamber, there's very little margin there. If we would have been working on the assumption that everything would be indoor, air-conditioned 20 C, right? But we knew that wasn't going to happen because we did a little background. And it's the same with, well, what's the amount of shock that occurs when you clap your hands? So we actually instrumented some stuff. And I found a really cool database that covered the types of forces people can do with grips and push and buttons and clapping. And then we measured it with the device, and we put some sensors on it and measured how much force it was getting. And so we went and figured out what our margin, or what our capability was, or what we expected the expected order of magnitude of these stresses that we're getting. Because I knew that if once we went to HALT, we needed to compare that to what we thought the environment was going to be, or the use case was going to be, as a starting point for us. do we have a lot of margin or not? And I expected to find a bunch of stuff in HALT because the design was it was pretty cool, novel, but there were so many ways we knew it could fail, from being stepped on, being dropped in the liquid on the table, to thrown through a TV,
Right. So, well, it sounds like a good approach, but I would say that's not the orientation of HALT, and that is looking at the strength of the materials and how robust you can make it with just using standard materials and standard materials and assembly methods. Okay.
Well, no, I agree with you.
So I would say,
but you still need to know what your technical. You still need to know. If we're failing at our technical limits of the materials, right? It's failing at 120, and that's the melting point for the polymer we happen to be using.
Right. If that's the plastic melting point.
But if our expected use is 115 C, well, then we got a problem. We got to change materials.
Well, for sure, with the materials of plastics and the material properties of plastic.
Right. That's
but
my
as far
example.
as FR4 materials, say that would limit. Okay, and this is where, this is where mechanical testing, vibration testing is absolutely critical.
Yeah.
Okay, and in fact, doing that when it's the controller is warm, 100.
When it's cold,
45, or when it's cold, right? Because either way, it could be that. But at the same time, the electronics, I would, remove from the case, and that's a very separate thing.
Yeah.
When you look at, so the two you look at from different, the stresses you look at for different things.
Yeah.
For me, now thermal stresses affect its function, the timings, the conductivity of the traces, and all that, and digital hardware and communication hardware that can be very critical. Yeah. So that's looked at it. I totally put it out of the case to do the stream testing without worrying about the melting point of the plastic. Just the FR4 material, which I know contains 200.
We're not designing one here, Kurt, but the idea is you need to think through it at that level. What are the types of stresses you're seeing? What are the ranges of stresses you're expecting to see? What are the failure mechanisms you expect? And even if you've never seen it before, how would you measure it? So if I'm looking at conductivity of the copper, and will that affect my packets resend rate on the Wi-Fi circuit, right? Mm-hmm. It's a signal that something's wrong with the timing. But how do you measure that when it's a handheld device inside a chamber? You got to think through all that stuff before you go to the lab.
You have to, absolutely. That's part of the planning. And in fact, my whole approach, what do you do before you actually have a product? Well, you have to plan what kind of tests you're going to run, what you're going to be looking for, where are you going to do it, if you have to set up a lab, if you have to get instruments like spectrum analyzers, oscilloscopes, and what test points do you have? Yeah. What functionality do you have with it? Where are your functions going to be most critical? You do the FMEA and kind of prioritize what section of the product you need to do. But again,
you just don't take 2 samples down in the lab. They put it in the chamber, shake and bake it for 20 minutes with it's not powered or monitored, and they bring it back to you and you test it. It'll probably work just fine.
Sure. Or you get, like one of my clients didn't really prepare properly and brought 3 samples with different operating systems, and there were different different development stages. And, there's nothing you can do to compare 3 different operating systems, or, and not all the same. It's just, and so why somebody, and I didn't get to talk to them.
So you got 3 single sample runs.
They said, we're going to have a HALT test down at, this lab. We'd like you to be there. And that wasn't useful at all.
No. Well, anyway, the idea of the question is, yes, there's a whole lot you need to do before you just take a couple samples down to the lab. It's
very much so.
And a good lab will tell you that. It's like, all right, now here's the checklist you need to go through before you come down here. The better labs will tell you that before they cash your check.
Exactly.
Kind of thing. So anyway, if your mileage may vary and you either have a good lab or not, or one in-house, but use it well. And that's through the planning.
Think about it. think about it before you go.
Yeah, exactly. All right. Well, thanks, Kirk. I knew that would get you going there. I knew that was going to be a good question for you. So anyway, if you've got a question, you'd like to join our list, we've got, we're getting close to our 800th episode, by the way, Kirk.
Boy.
So in order to make that, we need a few more questions. But in order to make the 1000th episode, we need 200 more questions to have topics and stuff. Otherwise, we just have to make stuff up.
Yes. And be aware that we have a wide variety of. Fred has such a great panel of people that know about all aspects of reliability, and that's where your question could be answered from so many different angles.
Yeah, and it's always a joy to, one, get your question and get you some response or answer, and then I bring it to somebody like Kirk, and we talk about it, and then I learn even more on it. So it's like, this is all good. I enjoy it. So please send your questions on over. Head over to accendoreliability.com/go/SOR, and you can find a couple of ways to get in touch with us. Kirk and I and the other hosts are all available through LinkedIn, which seems to be a very popular venue or medium or whatever that's called to get in touch with us, or through our about pages. Each of us have contact forms and emails and all kinds of stuff on our many ways for you to get in touch. So no excuse, if you got a question, if you have a question about one of the episodes or a question that you're struggling with at work or just curious about, let us know. We'd love to chime in on it. So with that, Kirk, I think we'll grab a couple of samples and drive off to the local HALT chamber and see what they can do for us.
I don't have the money for that.
Oh, okay.
That's expensive.
Yeah.
Anyway.
All the more reason to think about it.
And I do enough of breaking my own products in my own house.
That's right. Well, that sounds like a topic for another episode. All right, anyway, thanks, Kirk.
All right.
We'll talk to you soon.
Okay. Talk to you soon, Fred.
Yeah. Bye-bye. Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.